you for that welcome. Thank you for the applause. It's always nice to get a round of applause before I've even done anything. So let's see if it's the same at the end. So thank you very much for having me in Cadiz. It's a wonderful city. I've never been before, so I had a lot of fun wandering around, and hope to wander around a bit more before I go. So what I'm going to talk about is, so the advertised title here is Type-Driven Development of Communicating Systems. So communicating systems are, if anyone has tried to implement one, very hard to get right. So all kinds of things can go wrong. And what I'm going to lead up to is a final example where I show you one way, a relatively simple way, of using a type system to express correctness in concurrent programs. But that's kind of only part of what I really want to talk about. What I really want to talk about is the importance of totality, the importance of writing total functions, and the kinds of things that you can get, the kind of benefits you get if you write total functions. So I'll explain a bit more about exactly what I mean by a total function as we go. So Idris is a pure functional language with dependent types. It encourages what I'm increasingly liking to call type-driven development. So type-driven development, essentially, we're putting the types first and then deriving a program from the type that we begin with. Also, it supports totality checking. So this talk is about totality checking, how to write interactive programs if you have a totality checker, and as a key example, which I'll maybe spend the last 10 or 15 minutes on, how to use total functional programming to write type-safe concurrent systems. Now, concurrent programming, if you've ever tried it, you'll recognize it is a massive space. And I'm not going to begin to solve the problem. Well, I'm going to begin to solve the problem, but I'm not going to solve the problem of writing type-safe concurrent programs. Part of the reason I picked this example is occasionally I hear people say things like, types don't help you over a network, or types don't help you in concurrent programming. And this hasn't been true for a very long time. So if you go back to 1993, there's a very nice paper by Kohei Honda on called Types for Dyadic Communications. It's essentially introducing session types. So session types are a way of expressing communication patterns of programs. And this is back in 1993. So hopefully, as things develop, we'll be able to introduce these ideas into more mainstream programming languages. And people are trying. So, what is type-driven development? It's kind of important to know what that is before because this is all about starting with a type, driving the development of a program. So, instead of thinking of a type as being a thing that a machine checks and then tells us off when we get it wrong, the type should be seen as the plan for the program. So we say to the machine, here is what we're going to work on together. I say to the compiler, this is our job, this is what we're going to work on. So we write the types first. Then we'll define programs interactively, step by step, starting with our specification and making some progress towards a complete program. Those programs might be incomplete, so they might contain holes. So a hole is really something that stands for a bit of the program we haven't written yet. And the type checker will direct us to ways of filling in those holes with correct types. And quite often, if we're lucky, it'll be able to fill in those holes for us. And as we go, we'll often find that the type we came up with first isn't quite the type we wanted, and we might find that we need to tweak the program in certain ways. So we're refining the type and the program as necessary as we develop it. So the overall process, you've got to have a 3-word pithy phrase to describe a process, apparently. So I call this type, define, refine. We start with the type, we define the program, and then we refine the type and the program as we learn more about the problem that we're working on. So this idea of type-driven development, just to illustrate what's going on, this is type-driven development. So this is the contrast isn't great here. So this is from my new favourite pub in Durham City in the north of England, the Station House. It has a communal jigsaw. So you can see here the specification for the problem we're trying to solve, and you can see here the partial implementation with bits of the program that have been written. And then these are the candidate values that we're using to fill in the program. So after a bit of refinement, the picture that starts to develop, you start to understand what you're trying to do. And no matter how much you want to, you mustn't coerce values into holes where they don't fit. So I suppose you could, but get a pair of scissors out. But So the idea really is we're starting with a specification and we're trying to fill in something that works for that specification. The more precise the specification, the fewer programs there are that work, the more confident we can be that we've got it right. So actually there's a tired old analogy, isn't there, about bridge building and programming. So computer programming is not like building bridges. It turns out, so they're building a new crossing of the Forth, just north of Edinburgh, because there's too much traffic on the Forth Road Bridge. So they're building the Queensferry crossing. It turns out that building the Queensferry crossing is exactly like programming, because what they're doing is they're filling in the holes with some new values according to a specification. So you start to see this everywhere if you're thinking about building structures by filling in holes. So that's type-driven development. I'll show you how this works in a moment. But before I get to any examples of this, I think it's important to stress why I think total programming is important. So this is something we don't really talk about enough, at least outside of our own circles in academic events. So a total function is kind of fairly informal here, but you can think of a total function as being a function which is guaranteed to terminate with a well-typed result, or you might want programs which run indefinitely. So if you're defining a server, for example, or you're defining an operating system or a command line, a read eval print loop, you want those programs to run indefinitely. So you can also a total program is. You can also say that a total program is a program which produces a finite prefix of a well-typed, potentially infinite result in finite time. So like the first few elements of an infinite stream, for example. So why do we care? Why do I say totality is important? Why do many of us say totality is important? Well, if we care about types, we really ought to care about totality too, because if we think about what it means to write a type declaration. So if I have some function f of type t, what do I know about that, assuming it type checks? Well, if I know it's total, then you can look at that, say it's total, and that means that when we run f, no matter what well-typed inputs we give it, so I didn't give it any inputs here, but no matter what input it takes, it will always give a result of type t in finite time. So in a sense, it's a proof that this value t exists, and at runtime we will produce a witness of that proof. If f is partial, all we know is that under the assumption that f ever does give a result, that result will have type t. It doesn't tell us that we don't know that result is ever going to turn up, but we know that if it does turn up, it's going to be of type t. So I suggested that t stands for type. It could also stand for theorem. So given f of type theorem, if it's total, we know that it will always give a result of type theorem, so it's a proof of that theorem. And it's quite nice that the rooms here are called Curry and Howard, because that's exactly what's going on here. If your program, if your program is well typed and total, then it really is a proof of the theorem that you say it's a proof of. If it's partial, we merely know that if it ever gives a result, it's of type theorem. And at that point, I'm not so comfortable calling it a proof, because it's only a proof if we run it and it turns out to be a proof when we run it. So this is going to become important in the second half of the talk. So I'd just like to illustrate some examples of this, just so that you really get an idea of how the process of type-driven development works and how we do this totality checking in Idris. So I have... is that legible? It's quite hard to make this bigger at this stage. Some people nodding, great. So what I've got here is a definition of vectors. So vectors are lists with length. So the empty vector has length 0, the non-empty vector has length successor of k, given a tail of length k. So I can write a terminating, I should have taken that bit out. So I can write a guaranteed terminating, guaranteed total definition of the zip width function just by giving the type first and then interactively going towards a definition of that function. So I'm going to do this in Atom. You can do this in Vim or Emacs. I've started using Atom in talks because I find if I use Vim or Emacs, half of the audience get upset. Whereas if I use Atom, the entire audience gets upset, so it's all equal. So, including me, because I'm a Vim user. There. giving it away. So what I did there was I hit the keystroke for add definition, so add a skeleton definition. And you'll see this thing here. I was talking about holes. This is the piece of the jigsaw that we need to fill in. And I can look at the types of things in this setting. So if I ask for the type of the whole zip with RHS, Atom will tell me about that hole. It will tell me what's in scope and what I'm trying to produce. I can also inspect the things I have. So inspect the variables on the left-hand side of this. So I can inspect x's. I can case split on x's, and it will give me the two possibilities. So this is the type-driven approach. The compiler looks at the type of x's and says, OK, these are the possibilities for x's. Now what are you going to do? So let's look at the holes it's made, zip with RHS1. So given some y's of length 0, so this first argument, this list, or this vector x's, is nil. I've said in the type that the two vectors have to be the same length, so the type checker has said, OK, y's has to be of length 0. So what I'll do next is I'll say, OK, case split on y's. Tell me what the possibilities for y's are. So we'll case split on y's, and it only gives me one possibility. So this is part of totality in action and types for helping totality in action. The type checker has seen that there is only one possibility for this. So while if I'd given a less precise type for vectors, I would have been given the empty list and the non-empty list. I'm only given the empty list, and the type checker knows that this covers all the possibilities. Something else I can do with type-driven development is say, well, on the right-hand side here, we're looking for an empty vector. There is only one empty vector, so let's search for the empty vector, and it will produce me the empty vector. Similarly, in the second case, if I do a case split on y's here, x's was non-empty. They had to be the same length, so y's must be non-empty. And again, I'll say to the machine, I'm bored of doing jigsaws. Do the jigsaw for me, and it will. Because there's only because of the structure of the type and because of the type we're looking for, it will fill in a candidate solution for me. So this function is total, and you'll see this flag up here that says total. What this flag means is we're saying to the Idris type checker, after you've checked this function, if it turns out not to be total, this should be an error. So I'll show you. I'll show you how this works for a different definition. So I'm going to attempt to write a function which produces a value of the empty type. So void is the type with no values. So it's the empty type. And if I write a total function of type void, that means I can prove anything. Because if I've proved that nothing can something which can't exist can exist, then I have a contradiction. I can show anything. There is a way to write this. We can do some sort of non-terminating statement, like something like this. And if I load that into Idris, and so check whether the function I've just defined is total, it says. It's possibly not total due to a recursive path, due to possibly going forever. So if I then try to claim at compile time that this is total, then that becomes a type error. So Idris always checks whether definitions are total. But you're free to, if you're happy with this statement of partial correctness, that if your function produces a result, then it's the right type, then that's OK. But Idris allows you to say, I need this to be total. So it's allowing you to give the level of precision you want about the programs you're writing. OK, so that's about termination. But when we're looking towards writing interactive programs which run indefinitely. In particular, we're looking towards writing concurrent programs where maybe we want to start a process and know that we can always send messages to that process and we'll always get a reply. So we want these things to run forever, and I've shown you termination. So terminating things, well, they don't run forever. So this is where the other side of totality comes in, the idea of productivity, the idea of defining functions which produce a finite prefix of an infinite result. And a classic example of this is streams, infinite streams. So streams are defined in the prelude, and there is one thing I need to draw attention to in this definition. So it's essentially lists without the nil case. So I've got a value of type LM, and then I've got a stream, and this inf is it's a generic type, or a type constructor that says this thing is potentially infinite. This thing is allowed to go forever. And in practice, at runtime, this is like a laziness in the type. So it's like saying this is lazy, don't compute this until you need it. So I could define a function count from. Count from takes a number and then gives an infinite stream counting upwards from that number. That's the idea. So let's, again, do the usual thing of add a definition. And counting from k, the first thing is going to be k. And the rest of the stream is going to be, well, this type is inf. So inf has a constructor called delay. So we'll delay the construction of the rest of the stream. So let's, I'll load that in here, and let's not have Brexit. Did I say that out loud? Sorry. Okay, so we've loaded that in, and I'll just check that out. Confirm that I have loaded that in. And if I try at the REPL here, if I try running, count from 93, what I get is I get the first thing, so I get the finite prefix of the thing I'm generating, and then what happens at the REPL is you get what the type checker, the REPL evaluator does what the type checker does. So at compile time, the type checker will only evaluate the thing under this delay if it's forced, if you ask it to. So even though this thing looks on the face of it like it might run forever, here it's terminating. It's giving us a prefix. It'll give us more if we ask for it. So, natural question, how do we then ask for it? If I give some, I call it fuel. If I give fuel to this stream, then I can start generating bits of it using that fuel. And produce some result in some finite result. So first n will give me the first n things of an infinite stream. So let's just build that. So I want the first k things from this infinite stream. So I'll k split on k. The first 0 things from an infinite stream is the empty list. And the first successor of k things from the empty stream is the first value. And then the first k values of the rest of the stream. So let's try that. Let's take the first 10 things from that stream beginning at 93, and we see we get the first n things. So are these things total? So count potentially runs forever, but if I ask the totality checker, it said it's total. The reason it's total is that the totality checker knows that it's always going to produce something new, and as soon as something else comes along that you might want to terminate, so if something else comes along and asks for the result of that infinite stream, it knows that there's always going to be something available. So we've got this interplay going on between functions which generate stuff and functions which consume stuff. Okay. We'll move on to how that works for interactive programs shortly. But just to briefly say how totality checking works. We're looking for coverage. So in the zip with example, the type checker was seeing that we'd missed out some cases and checking that those cases are really invalid. We're looking for either termination, so there is a decreasing argument that gets us towards a base case of the recursion, or if there is a recursive call, then it must be guarded by a constructor. So it must be underneath a constructor, so there must have been a finite prefix. So that's type-driven development and totality checking. Type-driven development, essentially we know that it's looking for holes and finding things that fill in those holes. So that's what it's all about. Every time you see this, you need to think type-driven development, where's the hole that this value fits in, or what's the value that fits in this hole? If you want to learn more about type-driven development, by the way, a word from my sponsors. So there is a book in progress, very, very nearly finished. So you can ask me how to get a special secret discount code, and I'll tell you. So this is everything I'm talking about here about totality checking, termination, and the example with concurrency is in here. So much for streams, generating streams. what about interactive programs? So interactive programs, we are like, you know, concurrent programs, so we might want them to run forever. So, like Haskell, any Haskellers in the room? Quite a lot, yeah. So Idris uses I/O, so an I/O type for writing interactive programs. And I like to think of I/O as being, programs in I/O as being pure programs which describe the interactions that happen when that program gets executed. So they're pure right until the point that the runtime system gets its hands on it, or on them. So this program, hello, that reads in a name and prints out the result, it's a pure program because these are merely descriptions of the actions that get executed. So thinking of things in terms of a description of things that are going to happen, and then something that executes that description, I think it makes it a bit easier to think about how how productivity and totality works, because we're really thinking of making stuff and then consuming stuff. So this is all very well until you start wanting to write interactive programs which loop. So I've got a program here which is an interactive program which repeatedly asks for a name and then says hello to that person, just like a small child. What's your name? What's your name? And then it will, when it gets to the end, it will continue just asking for names. So the difficulty here is that this doesn't fit either of our definitions of totality. It doesn't fit the decreasing argument definition, the terminating definition, because right at the end it loops. Whoops. And it doesn't fit the productivity definition, although it will do shortly, we'll make it fit it shortly. It doesn't really fit the productivity definition because my intention for this I/O type, the way you should think of this I/O type, is being a description of terminating actions. So a description of actions which will eventually stop. We'll do some stuff, then it'll stop. So composing actions in this way might not be total, even if it's on the face of it okay. I mean, this program is clearly okay. It's clearly a reasonable thing to run. It's going to do something before it loops. We're going to get some response out of it. We're going to get some interaction out of it. So the question is, how do we convince Idris, or how do we convince any language that does totality checking, that this is an okay thing to do? We're going to have to do this kind of thing if we want to write real programs. So a solution is to think of these looping programs kind of as a stream of I/O actions. It's not really a stream. It's more like an infinitely branching tree. An I/O program which runs indefinitely. So this is an idea, I think, due to Anton Setzer. The idea that you can make you can use infinite streams or infinite data structures to describe infinitely running programs. They're merely descriptions of infinitely running programs. We'll run them later, and we get an initial action. So this IOA, we know this terminates because I've defined that IO is the type of terminating interactive actions. And then the rest of the program is a function which is computed from the result of that initial action, and it's going to be a potentially infinite program. So the way that looks, it's probably better just to show you this than go through slides. I mostly put these things in slides because people keep asking me for my slides, and I only give demos, so now I've put them in slides, so you can ask me for the slides and hopefully get something. So the way this works, or the way this works when we write the program is, this function definition here, this is to give us do notation. So Idris has a rebindable do notation, just like I think one of the Haskell extensions gives you rebindable do notation. So it's a way of having do notation if the type you've got doesn't fit the monad type class. So Idris does have type classes, but we're not using them here. So now we have this potentially loopy this loopy program. So reads a name and prints a result and then loops. But if I load this into Idris now, what did I call it? IO stream, I think. If I load it into Idris now, it will say, yes, that's total. The reason it's total is that before I do this, before I produce the rest of the infinite sequence of actions, I'm doing stuff. So as long as I do stuff before I go on forever, I'm producing the finite prefix of the infinite sequence. So we're fine, we're good. We do, however, have to run these things. And this is where things get a bit tricky. So we have to run the things knowing that we have, remember I talked about fuel. I talked about when we consumed things from the infinite stream, I talked about giving some fuel to the stream being the number of things we have to generate. So what I could do is when I want to run this is say, just skip down to the end here, I'll skip the intermediate definition. Say that running this thing is going to turn our infinite stream of I.O. into an I.O. action, and I'm going to tell it how long it's allowed to run for. So we're not quite at infinitely indefinitely running programs yet. We are still giving, we're defining some kind of fuel tank for this that says how long we're willing to run it. I can show you that in action. I'll move this up a bit so you can see it. I'll give it 10 iterations in the fuel tank. Fred, Jim, Sheila, and it's out of fuel. If anyone knows why I use the names Fred, Jim, and Sheila, by the way, come to me and I'll buy you a pint. It's a challenge for today, or coffee, whatever your tipple of choice is. So it's got to a point where it's run out of stuff. It's run out of ability to do things. So I can check that run is total, so that's fine. Loopy is total. Run is total. The generation of infinite actions is total. The way of executing those actions is total. It's just that we still have to give some number, and it doesn't matter what that number is. If it's big enough, it will run forever. So this is where we introduce one tiny little hack into the system. And we need, at some point, this is kind of unavoidable. The runtime has to know how to get these things to keep going. Has to know how to keep generating the ability to execute this infinite program. So we have one partial function that says, when you need fuel. So I guess I could call this solar energy or something, which isn't quite forever, but forever as far as we're concerned. So when you need some fuel, it's okay to make some more. So you need to give some kind of way of saying this program is going to run forever, but all of the machinery that allows the program to run forever, all of that is total. And as long as all of that is total, we can be confident that the programs we're writing do what we want them to do. And have the type. The fact that they have the type they have means that we really will get that infinite sequence of I/O actions, and they really will get run. Okay. So why did I tell you about all of that? The reason I told you about all of that is because I want to show you, given all of that, how we might start defining types for concurrent processes. And like I say, this is the simplest way I could think of doing it. And still be confident that it was doing the right thing. So, the Idris runtime system has, sort of inspired by Erlang, it has it has separate processes. Each process has its own internal heap. Each process has a mailbox. So you can send messages to those mailboxes. You can see what's in your mailbox asynchronously. Now this is completely ill-typed. There's no type checking going on here. So if we want to have some kind of type-safe concurrency mechanism, we better think about how to type check these things. So you could do something like Cloud Haskell does, which is there are dynamic type checking. So when you receive something and say this is a particular type, then you will check that type, and if it's the wrong type at runtime, we'll give up. But I want my programs to be total, and I want to know that they're going to do the thing that I say they're going to do. So I'd like a bit more precision. I'd like to be able to express the types of interactions that are going on. So what I'm going to show is a very simple way, or very simple is a bad word to use, a very small way of describing one kind of interaction. And we'll maybe briefly mention some ways we could extend that later on. So on top of this mailbox system, where we're sending messages asynchronously, we've got a library which allows processes to spawn processes. It allows processes to create channels. So channels, you can connect to a channel and send a message on it. You can create a channel by listening for incoming messages, and then once you've got that channel, you can send messages back and forth between processes. So Go has a mechanism a bit like this with type channels. I think the way it works in Go, the channel has a particular type, and you can only send values of a particular type on that channel. I think that's a bit of a shame for a lot of concurrent programs that you might want to write, because they might go in this kind of pattern. You might spawn a process. So this is, on the left here, we've got a main program, and that main program here has spawned a process called adder. Adder's job is to sit there in the background waiting for requests to add two numbers. So it's not a particularly big concurrent process, but it's a kind of pattern that you might use if you're writing something with lots and lots of processes like Erlang or Elixir. You'll write processes that have a particular job. You'll send it requests. You'll get responses. So the type we're sending a message saying I want you to add these two numbers, and we're getting a response of just a number. So the message and the response have different types, and this interaction only makes sense really if main sends a message and then receives a reply. And it only makes sense for adder if adder receives a message and then sends a reply. So if we get any of this ordering wrong, bad things are going to happen, so programs might deadlock. If we get any of these types wrong, bad things are going to happen because we're going to treat things in ways that they're not supposed to be treated. So how might we express that in the type system? How might we use an expressive type-level language to say what's going on in this kind of program? So we'd kind of like to ensure a few things about our programs. We'd like to ensure that when we send a request, the response we get is going to be well-typed with respect to the request we sent. So if we send a request of type add, we want the response that's going to be the result of that add. It's just like input types and output types of a function. This is something that's completely natural to us when we're writing sequential code. We also want the server to know that when we send a message to the server, that process is still running. So ideally, it's going to be running indefinitely. If it's not running indefinitely, we might spawn it and then send a message to it, by which time it's quit, and we're not going to get a reply. So that's where the productivity comes in. But also, we want to know that the server is guaranteed, while it's running, it's got to be guaranteed to respond to a request. A server that runs forever but never processes any input isn't much use to us. So every time it loops, we want it to at least process one request, because if it runs forever, processes a request on every loop, we know it's going to always respond to the thing we're sending it. So I'll show you an example before I show you this. So I'll show you how the programs work. So this is our adder process that accepts requests of a particular type. So it accepts requests of type of the form add nat nat. It accepts requests that add two natural numbers. And then we define a type that says, for that particular request, this is the type of the response. So if we get a request of type of the form add xy, the response we send had better be a nat. So when we define our server processes, we have to say what kind of requests and responses they're willing to work with. So we only give the response type because we can work out the request form from the response structure. But so this response thing essentially defines the interface that this process is willing to work on. So accept will sit there waiting for a message. So it'll time out after a second in this particular implementation, but it'll sit there waiting for a message. When it gets a message, we define a function that says how to respond to that message. So if we get a message with the form add xy, we have to return something of type nat. And then this loop says we're going to run forever. So loop is a constructor that it's kind of like the cons constructor in a stream. It says now go on forever. Now continue running rather. And then when we start a client, when we have a client, the client has a reference to the server. So this server will respond on this interface, and we'll send messages to that server of the appropriate type. So if we get any of these types wrong, if I send a message of the wrong form to this server, I'll get a type error. I guess I could run that. We like running programs, don't we? That's kind of why we write them in the first place. you know, it type checks, so, you know, it's clearly fine. But let's run it anyway. So all this does is it takes some input, and there is, I promise you, there is a process running in the background. If I give it a number, it will add something to that number. I'll add 94 to that number. I did promise you, I can actually prove this. I can make this say that it's waiting for some input. So it's sitting there waiting until I give it a number, and then it will do something with that number. So if I were to do something like forget that this thing is supposed to run forever, we don't want this. In the description of processes I've given you, that doesn't make sense. Something shouldn't stop responding to messages. So one would hope that this doesn't type check, and it doesn't type check. The reason it doesn't type check is, well, the reason it doesn't type check is that state machine. So servers have to follow a particular sequence of states in order to be, you know, helpful, in order to be the kind of thing we want them to do. So they start in a state where they're ready for messages. They move on to a state, once they've responded to a message, they move into a state where I've now responded to a message. I can respond to more messages, or I can say that I'm done. And if I'm done, I move into this looping state. So a server process is only valid if it starts in the ready state and ends in the looping state. So I can define a type in such a way that if I don't do the response and if I don't do the loop, it's not a valid process. Now, I'm nearly out of time. In fact, I pretty much am out of time. So I just want to show you how that is defined, how that type is defined. Because you might think that I mean, these client and server processes, they're just a small fragment of the kind of things you might want to do with concurrent processes. But on the other hand, they do open up some fairly large space of implementation patterns you can use. So it's type safe, it's total, therefore we know it behaves the way we said it's going to behave. And the question is, how much work is it to implement that process type? So you might think this is going to involve some incredibly complicated type-level gymnastics. Well, that's maybe open to interpretation, what you think of incredibly complicated type-level gymnastics. But the pleasing thing is that the definition of processes and the interpreter and the run function for that interpreter is only 90 lines of code, or 92 lines of code, which I think is quite nice. I think it's quite nice that you can come up with this description of type-safe concurrency, admittedly limited type-safe concurrency, but it only takes a small amount of code to be confident that your programs are going to behave the way you want them to. Okay, I will. As far as the code goes, I'll stop there. Just to say a couple more things. We've seen concurrent processes in action. So there's loads of places you can go to learn more about what's going on here. So I've only really touched on the kinds of things that you might want to do. And I think, you know, when people like me come along to places like this, it's probably a good idea to show you where you can go, where the accessible places are that you can learn about why totality is important, why types are important. So this paper by David Turner, I particularly want to mention because it's one of my favorite papers ever. It explains why totality is important and how to write total functional programs and why this is the future. So it is highly accessible. I highly recommend reading it. Also, I said that this space of types and concurrency was massive. It truly is massive. I've just picked out 3 here, just sort of to hope are representative. But I'll put the slides online. I'll tweet them afterwards. And if you want to go and look at these things, then you can. OK, so just to summarize, I showed you concurrency as the example. The only reason that example is something we can believe these programs behave the way we want to is because we have totality. So these processes have to respond to requests. The requests are terminating. The processes themselves are productive. And this for concurrent programming, I think one useful pattern is to define a server process and then write a program just as a collection of clients, each of which can talk to this server process. Using dependent types, we can describe these processes really quite precisely. So there's a whole lot more stuff to do here. So one thing we're particularly looking at is taking session types and having more interesting interactions between clients and servers. I think we can go a long way with defining security protocols that way, with being sure that a security protocol follows what it's supposed to do from start to end and doesn't do something like, I don't know, go to fail twice. So this is the sort of thing that we can encode if we have a precisely enough type system to say that we're following this process and we always continue running. Okay, so I'll stop there, and thanks for your attention, and I'm happy to talk to you throughout the rest of the day. Thank you.